Welcome to the last session of HoTT-UF, and Pietro is going to talk about topological reading of inductive and co-inductive definition.
Thank you for the introduction. So, in our work, we want to compare the so-called inductive and co-inductive methods of formal topology with other well-known established scheme for induction and co-induction. In particular, with inductive and co-inductive definitions in the sense of Axel, with well-founded trees and non-well-founded trees in Martin-Löf type theory. And we will see that also higher inductive types will begin. And maybe higher co-inductive types, I don't know. This will be a question to the audience. So, first of all, what is formal topology? Well, the idea is to study topology in a constructive and predicative setting, like homotopy type theory, for example. In order to do so, you need, first of all, to reverse the conceptual order of, let's say, traditional topology. So if in classical, traditional topology, you start with a set of points, and from there you define what does it mean for a subset to be open, and then you can also define the notion of basis for a topological space. In formal topology, your primitive notion is that of basic open, is that of a basis. And then you go on by defining as a derived notion what is an open or closed subset, and at a very later stage also what is a point. Sometimes formal topology is referred to as a point-free approach to topology, but this does not mean that points do not exist, but they are just not a primitive notion in this setting. Oh, right, a warning. It seems that this reversing the conceptual order, it is not a matter of taste, but it seems like the only thing we could do if we want to stay predicative. Okay, so what is a topological space in this framework? Indeed, it is just a set whose elements are thought of as basic opens, and two relations between basic opens and families of basic opens. The two relations are called basic cover, A covered by V, and positivity relation, A fish V, because it resembles a fish, that's all. I don't want to spend too much time on the axioms here, just notice two things. First, the axioms of the basic cover have a kind of an inductive flavor, while the axioms of a positivity relation have, as their names suggest, a co-inductive flavor, and we will see we can exploit this fact. And the special intuition is the following. A covered by V simply means that the open A is contained in the union of the family V, while A fish V means that there exists a point, and notice I didn't define formally what a point is. This is just intuition, spatial intuition. There exists a point in A, all whose basic neighborhoods are in the family V. Okay, so one really important method of this field of formal topology is the following. We want to generate examples of topological spaces inductively and co-inductively. The idea is very simple. We start with a so-called axiom set, which is a set of axioms. So it is just for each basic open, we want a set of indices, and for each one of those indices, we want a family of basic opens. And then we go on by inductively defining the smallest basic cover satisfying those axioms, and dually co-inductively the greatest positivity relation satisfying those. Okay. The key point here is that this kind of induction and co-induction are predicatively sound. We can do it predicatively. And they actually satisfy all the list of axioms. So great. Oh, sure. And then we can show that formal topologies generated in this way satisfy nice properties. A lot of natural topologies arise in this way. So it's a really important method. And so a natural question is, does it relate somehow with other form of induction and co-induction? In order to discover this fact, we need, first of all, to formalize those methods. And the formalization was first performed in the minimalist foundation. So let me do a brief digression on the minimalist foundation here. The minimalist foundation is a dependent type theory introduced with two goals in mind. The first one, indeed, is to have a framework in which to do formal topology. Historically, formal topology born in Martin-Löf type theory, but then it was soon realized that Martin-Löf type theory is excessive in a way because, for example, you have the axiom of choice. While in the minimalist foundation, you can think of it as a version of Martin-Löf type theory in which you have a primitive notion of proposition. You can do formal topology as well with less proof theoretic power. Okay, and the second goal of the minimalist foundation, as hinted by its name, is the fact that it can be taught as a common core among all the foundations of mathematics. This means that if you write down a definition, a theorem, or a proof in the minimalist foundation, then you can export it to your favorite foundation. For example, homotopy type theory. So the co-inductive methods of formal topology were formalized with two constructors, an inductive type constructor and a co-inductive type constructor. But they are not just type constructors, they are propositional constructors. So since we are generating relations, so something that live in the logical realm, not in the set theoretical one, they are not just general type constructors, but they are propositional type constructors. So just like the existential quantification and so on. Okay, why am I stressing all of this? Because now, if we want to export our definitions from the minimalist foundation into homotopy type theory, we have two choices. The first one, since we know that the minimalist foundation is compatible with homotopy type theory, we can take this lower path and directly interpret each proposition of the minimalist foundation as an H proposition of homotopy type theory, straightforward. But since the minimalist foundation is also compatible with Martin-Löf type theory by collapsing the notion of proposition and generic type, we can also make a detour through Martin-Löf. And then, since we know that homotopy type theory is just an extension of Martin-Löf, go back here. Notice this triangle is not commutative because if we start with, for example, if we start with an existential quantifier here, it will be translated first here as a sigma type and embedded here as a sigma type. But if we take the lower path, we will end up with a truncated sigma type, okay? So, in homotopy type theory, we get two versions of our inductive and co-inductive topological constructors. A proof-relevant version, this one, the higher path, and the proof-irrelevant version, the lower path. Okay, and the idea now is very simple. We want to compare the proof-relevant version with proof-relevant stuff and the proof-irrelevant version with proof-irrelevant inductive and co-inductive schemes. So let's start from the proof-relevant case. The obvious term of comparison here is given by trees. Well-founded trees in the case of the W-type constructor, or not necessarily well-founded trees in the case of the so-called M-type constructor. I will recall their definition through their categorical semantics. This is also the only thing you can do in the case of co-induction. So Very briefly, recall that a polynomial endofunctor in a locally Cartesian closed category is nothing but a functor isomorphic to a composite of this form. So you start by, well, you need to start with a so-called polynomial, so a diagram of this shape. Then you start, first you pull back along H, then you take the dependent product, and then the dependent coproduct. The idea, of course, these, let's say, syntactically correspond to a so-called indexed container, so a container with an extra dependency. So the definition of semantics is the following. Indexed W types, here I'm referring only to their indexes versions, or also known as dependent versions. Indexed W types are just initial algebras of polynomial functors, endofunctors, and dually, indexed M types are terminal coalgebras of polynomial functors. Pretty simple. Okay, so what's the result in the proof-relevant case? In a previous work with Maietti, we showed that in Martelov type theory with function extensionality, you can prove that actually W types and proof-relevant inductive basic covers are define the same scheme, have the same expressive power, if you want. Formally, this means that they are mutually encodable. Now we upgrade this to the coinductive case by showing that proof-relevant coinductive positivity relations are definable through M types. But notice that here we do not have the opposite direction, so we do not get a full equivalence. I will try to show you why. It is pretty expected from the definitions of the two schemes. But first of all, let me show you this straightforward corollary. Homotopy type theory supports, thanks to the results in this paper, because homotopy type theory has M types, supports the proof-relevant inductive and coinductive methods of formal topology. So you do not need to postulate them in homotopy type theory. It is already powerful enough. Okay, so the idea of the proof is the following, and I will phrase it again categorically, but the proof actually is done syntactically. There is also an AGDA formalization. So recall that this is the definition of polynomial endofunctor. We need to introduce a new definition, slightly modified, of copolynomial endofunctor. It's very simple. You just swap the role of the dependent product and the dependent coproduct, nothing else. And then the two main observations are the following. First, proof-relevant inductive basic covers are initial algebras of polynomial functors, so just as W types. And for this reason, they are totally equivalent. But proof-relevant coinductive positivity relations are terminal coalgebras of copolynomial functors. So while M types and W types are defined referring to the same class of functors, here, when we go from, in the topological methods, when we pass from the inductive case to the coinductive case, we dualize also the class of endofunctors we are referring to in the definition. And the second key point is that at the end of the day, copolynomial functors are a subclass of polynomial functors. And for this reason, you get this asymmetry. You get only one direction in this second theorem. Okay, that's for the proof-relevant case. For the proof-irrelevant case, we looked at an established notion in set theory, axiomatic set theory, due to Axel. And it is really simple. It just formalizes the following idea, that if you have a kind of internal deductive system in your theory, so a set of inference rules of this form. This is something internally in your system. So we have rules with a conclusion and a set of premises. Then you want to consider the subset of derivable elements of this internal deduction system. So you can thought of it as the subset of theorems. And this is done inductively, of course. And you can also consider the subset of positively confutable elements. So elements that you can constructively prove they can't be deduced with those rules. The formal definition first appeared in Axel, again in ZF, then Ratien generalized it to constructive set theory, and we adapted the definition in the minimalist foundation. So now we can again export this definition to homotopy type theory, Martin-Löf type theory. Okay, so the result in the proof irrelevant case is very nice and tight, because we showed that everything is equivalent. So inductive basic covers and inductive definitions of Axel are really the same thing, and the same goes for coinductive positivity relations and coinductive definitions. And notice that this theorem holds already in the minimalist foundation. So trivially, it holds, automatically, it holds also in Martin-Löf type theory, in homotopy type theory. But here's the catch. Are proof irrelevant methods of formal topology supported by HoTT? Well, for the inductive case, luckily, yes. This was already observed by Kokand and Tosun, that in a work in which they formalize a bit of a formal topology in a Univalent foundation. So the idea here is to use quotient inductive types. You want to define inductively a type constructor, but simultaneously you want it to be an H proposition. Okay. What about proof irrelevant coinductive positivity relations? Because here it is not clear how we can do this, because we would like to coinductively define something, but at the same time, we want to end up with an H proposition. And let me say that the naive way of just taking an M type and truncating it does not work, because truncation, let's say, does not preserve terminality. And so this is really my open question to the audience, if you know any possible solution to this problem. Otherwise, we need to postulate proof irrelevant coinductive positivity relation in homotopy type theory. And that's all. Thank you for your attention.
Thank you. We have some time for questions.
Yes, thank you for your talk. Yeah, just a comment to your last question.
Yes.
So what you do is, when you define co-inductive types, you think of destructors, right? I mean,
yeah.
It's not the way you present it, but that's the way to view it, right? And if you think about, so there's always, you can always define a category of algebras, and you can define a category of algebras including this property of being an H proposition. And you take the terminal coalgebra of this. So this is basically what you also mentioned at the beginning, is a higher co-inductive type.
Okay, yeah.
So they're not in the moment sort of included in
okay.
HoTT, but it's a good point. That's exactly what you need here. If you want to truncate a co-inductive
definition. Yeah, okay, perfect.
It's a valid destructor. I mean, forcing something to be a proposition or a truncation is both a constructor but also a destructor.
Okay, thank you. Thank you.
Hi, thanks for your talk. So I'm curious about these copolynomial functors.
Yes.
Are these? Is this like is this a studied notion? Do we know like how these behave, or I mean, because polynomial functors are, there's a whole literature on them. Is Yeah, do you know much more about these, or?
No, I invented this
Okay.
notion.
Yeah.
So no,
Do you know if
I
they
try to look if it was already existing out there, but no. So
Yeah.
I made it up.
Do you know if they admit like a nice presentation in the same way that polynomial endofunctors have containers? Do you know if there's like a co-container?
The container, well, the fact is that the container is the same for both. Because you start, well, I did not report here in this slide, but they both stem from the same polynomial. So from the same index container.
Thank you. Thank you. So maybe just before I go to the other thing, just on this, so what you can look for is what is called cooperators.
Cooperation, okay.
So it's something that has been studied in the world of coalgebras, actually, for exactly this purpose, that when you have coalgebras, you do exactly the dual kind of thing to what you do with algebras.
Okay.
But so more on the first thing, so I wanted to mention that I had at some point a student that didn't go very far, but who was studying what you may call high inductive types, but we call them actually sub-co-inductive types.
Sub-co-inductive types.
Why? Well, the idea is that if you look at higher inductive types, they represent some form of co-limit. Right? So what would be the dual? It's a limit. So you look at sub-objects of some kind of product.
Okay.
And what you get then is you get types where you actually have that the proof that something is in your type becomes not used in the comparison of elements. Right? So the equality relation becomes agnostic to proofs. In comparison to sigma types, you would compare these things. And that's exactly what you want, right? You want to have then propositions. When you start with a proposition, you still ignore afterwards the proof that something is in your type. So that's basically
okay.
I think what you were looking for. But
great, I will look at it. Thank you.
So thank you very much for your talk. It was very interesting for me, and actually what you say too. So my question is, so when you use Axel and Ratian,
yes,
inductive and co-inductive definitions, so actually they depend, am I right, and non-well-founded trees actually, do they depend, this is based on the non-well-founded axiom by Axel, am I right?
Yes, let's say that, where are they? One moment.
Yes.
Yeah. To formalize them in constructive set theory, you need some extra axiom, the generalized dependent choice.
Yes, I know.
Yeah. Okay. And because you need generalized dependent choice just to formalize the concept in constructive set theory. But then, in order to show that these two subsets are actually sets and not just classes, you need also another regular extension axiom.
Okay.
So, yeah.
Then I have vague suggestion and guess, but I'm not expert. For many years, I didn't look on the topology. So actually, it looks to me that the inductive definition is based on the minimal fixed point.
Yes.
And the co-inductive on the maximal fixed point. And how you truncate it, it looks to me, but maybe you will over-truncate it, because that's what I do myself right now. I'll present it tomorrow. But in recursion theory, in type recursion theory, I did it also in a dependent type theory many years ago in my dissertation, and now I'm restarting it. It's actually Muscovakis figured out, and after 2006, I took it and started and developing it. Actually, he introduced a very nice definition for the termination.
Okay.
I'll present it tomorrow if you come, but there is a very, it is by Muscovakis, so trust him. but I develop it and to make it more suitable for the dependent type theories.
I will be here tomorrow, so I'm looking forward.
Tomorrow it's in the simple type theory because the
Okay.
difficult point is to develop the theory itself.
Okay.
With the most difficult case. The most difficult case is actually this to maintain this acyclicity, the termination, the machinery to be developed recursively and inductively, so that so that the machinery is that lifted easily.
Okay, thank you very much.
So let's thank the speaker again.
Thank you all for the useful suggestions. Thank you.